Creating false memories. Our experiences and memories of them make us who we are. Some health conditions can affect how reliable our memory is, but even a healthy memory isn't necessarily a perfect recording of things that actually happen, and are more our own take on things. Amazingly, memories can even change over time as we recall them. We still know very little about how our memory actually works. The authors of this review, Ramirez and colleagues in 2014, were trying to shed more light on this. They explain how we also don't really know where exactly in the brain the memory sits and what a memory looks like, despite there being scientific studies that give us hints and clues. One thing that most studies agree on, though, is that part of the brain called the hippocampus remembers the situation and where we were in time and space. Our understanding of the process that creates new memories used to be that cells that fire together wire together in a network of what looks like millions of tiny electrical wires that connect up in our brain, as suggested by Donald Hebb back in 1949. But now we know that the brain can also rewire itself in a process called plasticity. Now, if you want to find out what the biological process is leading to the creation or experience of our memories, then you need to look at three things. You need to check which brain cells are being switched on when memories are being created. This is called correlation. Once you think you know which cells are active during that memory, you then need to try to stop the biological process from happening to see if memory is still being created or experienced. This is called a blockade. If both of these things happen, then you also need to show you can artificially switch on the cells to see if this triggers the memories or learning you're interested in. This is called mimicry. It turns out there is support from scientific studies for 1 and 2, though this has mainly been done with animals and not humans. But number 3 is still a bit of a problem. It's very hard to select, label, and then switch on particular cells to see if this results in learning behaviour.
Luckily, we have CFOS, a detectable protein that neurons produce when a memory is created. By looking for the CFOS, we can now measure traces of cell activity after they've been switched on, and label them with the photosensitive molecule called channel rhodopsin. These molecules produce electricity when you shine light at them, which activates the neurons they're attached to. So now we can activate the labelled neurons with light. Of course, it's difficult to shine a light into a mouse's brain, so we use a fibre optic cable.
Often researchers will look at fearful behaviour to test if learning happens, because fear is easy to see in animals. If you put a mouse into a box and give it an electric shock, it will freeze in fear, and a negative, fearful memory of that box will be created. When you put the mouse back into the same box later, it will freeze because it remembers what happened last time it was in the box. If you put the mouse into a new and completely different box, the mouse won't become fearful. Interestingly though, if you turn on the fear memory when it sits in the new box, using the injected switch, then it freezes in fear. Next stop, Inception. It gets even cooler. Not only can you switch on memories in mice, but it turns out you can even create false ones. If you keep switching on an old neutral memory created in a previous place, in a new place, and pair it with an electric shock, the mouse will suddenly become fearful of the previous place too, despite having never received a shock in there. The original neutral memory has turned into a false, fearful memory. Now, that's the stuff Hollywood movies are made of, isn't it? So creating false memories is a thing, although currently we don't know how well these findings in mice are true for humans. Memories then aren't perfect reflections of what has happened. We unwittingly change or adapt stories over time and to fit with what seems logical to us and the situation. This also means that the more fluid nature of memories can be tinkered with. Our understanding is growing in this area, and there's lots more research to be done to see if we can delete or edit memories in humans, which could be very helpful in treating conditions such as post-traumatic stress disorder. The presented research can help us develop treatments for conditions in which memory is impaired. It can help us understand where and how memories are formed, and potentially shed some light on complex processes such as anxiety, depression, and social interaction.
What uses can you think of?